recall our work from last time. We have G of finite group. We have pi v, pi prime v prime, unitary representations of G. A problem, we want to understand L2 of G in terms of the representation theory of G. So L2 of G is the vector space of complex valued functions on G. L2 denotes that we're norming using the L2 norm. And if we consider the right or left action on L2 of G by the group, we have a unitary representation. Now, when G was finite abelian, the characters were enough to understand L2 of G. So we had an orthonormal basis of L2 of G given by the characters. So we only need the one-dimensional representations. For general G, okay, the one-dimensional representations are not going to be enough. So we also need to consider irreducible representations with dimension greater than 1. Now, how do we get functions from these irreducible representations? Well, if we take a pi v, I fix a basis for v, then each pi g is represented by a square matrix. We fix an entry, say the ijth entry, and then let the elements range over the group. So in the ijth entry, as each group element changes, the value changes, and we get a function on the group. So that's what we're calling a matrix coefficient. Formally, if we have u and v, I'll define phi sub uv from the group of the complex numbers as follows. So if I evaluate a g, we're just taking the inner product of pi gu with v. Now, our main result from last time, we had the Schur orthogonality relations. So if we assume pi prime are also irreducible, okay, we form matrix coefficients for each. We take the inner product in the L2 norm, okay, given as follows, and then we get this expression here. So if our representations are the same, we get this gadget here, and last time we expressed this as an inner product on a tensor space. If the representations are inequivalent, we get 0. If they're equivalent, we use this gadget here, but we have to stick in the equivalence. Now, you'll note with this, okay, what I can do. Well, we'll take an irreducible representation pi v, we'll choose an orthonormal basis for v, then we're going to form the matrix coefficients associated to this basis here. So this is going to give us a set like this. This is going to be an orthonormal set if we scale. Okay, you note how many elements are in here? Well, we have dimension v, so dimension v squared matrix coefficients giving an orthonormal basis of the matrix coefficient space. If we sum over, okay, take the union over all irreducible classes for G, we're going to have an orthonormal set in L2 of G. And we can hope that that's going to be a basis of L2 of G. Another consequence, okay, if we count, well, if I sum over all irreducible classes, okay, we have dimension squared here. Note, the dimension of L2 of G is just the order of G. So we have this inequality comparing the dimensions to the order of the group. If we have a basis for L2 of G, then we have equality here. Now, our main theorem, we have completeness of L2 of G using matrix coefficients. For general compact G, we call this the Peterbile Theorem. Statement, as representations of G cross G, L2 of G is equivalent to this orthogonal direct sum. So the sum is going to range over the irreducible classes. Okay, we pick a representative for each class. Then we take that representation, tensor it with its dual. To pass from right to left, we form matrix coefficients. If we take this action over here on the right, that's going to intertwine with the right action tensored with the left action on functions. Now for the previous board, an immediate consequence, the order of the group is equal to the sum of the squares of the dimensions for each irreducible class. Okay, so to check for S3, order of the group 6, we have trivial, sign, and irreducible two-dimensional, so this checks out. Now for a proof, we approach it in 2 steps. For the first step, okay, we'll take any representation, pi v, not necessarily irreducible. If we form matrix coefficients, okay, then each matrix coefficients can be written as a sum of matrix coefficients for irreducible representations. Now to get this, we just invoke full reducibility. So we can take v decompose it as an orthogonal direct sum of irreducible representations. So if I form matrix coefficient, okay, using elements of V, we can decompose V and W into sums according to full reducibility. Then if I expand that out, the resulting matrix coefficients are just going to be those for irreducibles. So we have this step. For step 2, show that any f in L2 of G can be written as a linear combination of matrix coefficients. Then by part 1, linear combination of matrix coefficients of irreducibles. Now, that shows that our orthonormal set is also spanning. To show this, I'm going to choose any orthonormal basis h sub I for L2 of G. So that means we can write any h in L2 of G in this form here. Now, if we let h be equal to the right action of G on F, okay, we evaluate that at x. I'll have f of x times G. Then using our expression here, we get this. If I let x be equal to the identity, okay, what happens? We have f of G on this side. Over here, h sub I of the identity is just some number. And then we have matrix coefficients for the right action of G. So that expresses f as a linear combination of matrix coefficients. And that gives our theorem. Now, first consequence for analysis, we have Fourier's trick and Parsifal's identity. So we have an orthonormal basis for L2 of G now, in terms of the matrix coefficients. So that says every f in L2 of G can be written in this form. So we have elements from our orthonormal basis for L2 of G. The way we get the scalars in front, we just take the inner product of f with elements from the orthonormal basis. Then we also have, if I take the length squared of f with respect to the L2 norm, it's equal to the sum of, okay, the moduli squared of the coefficients. Let's recall another result from last time. If pi v is any unitary representation of G, could define the character of pi. So the character of pi on G is just equal to the trace of pi G. If we choose, okay, u sub I, an orthonormal basis for V, okay, then each pi G is represented by a square matrix. Then the trace is just the sum of the diagonal entries. Okay, and we can write this in this form here. Now, these are matrix coefficients for pi, so we can apply Schur orthogonality relations. So we get Schur orthogonality relations for characters. So if pi and pi prime are irreducible, okay, I take the inner product of the character of pi with the character of pi prime, okay, L2 of G. We get 1 if pi and pi prime are equivalent, and 0 otherwise. So we note the characters of the irreducible representations are going to form an orthonormal set. Now, if we want orthonormal basis, okay, we have to put this in context. So what space would we be looking at? We're interested in the space of class functions. So I define class of G. It's going to be all f in L2 of G, such that f of gx g inverse is equal to f of x for all x and g in our group. Now, one way to interpret this, f is constant on conjugacy classes. Okay, and recall a conjugacy class, okay, conjugacy class of x, just given as all conjugates of x as we range over the group. Now, we have an obvious basis for the class functions on G. Okay, I'll take f sub x, okay, where x represents each conjugacy class in G. We'll let f of x on x prime be equal to 1 if x prime is in the conjugacy class of x, and 0 otherwise. Now, because the conjugacy class is partition G, this is going to give us a basis for class G. This leads to our next theorem. We've seen that the irreducible characters form an orthonormal set in class G. In fact, they form an orthonormal basis. Because we have two orthonormal bases, okay, we could just count the number of irreducible classes of G is equal to the number of conjugacy classes in G. So, for example, if we take S3, we have 3 conjugacy classes given by cycle structure. We also have 3 irreducible classes of representations. Now, I'm storing all of our information in what we call a character table. So when we're working with non-abelian groups, what we'll do, okay, so each row is going to represent an irreducible representation. Okay, the entries are the character values. I don't need a column for each element of G. I just need a column for each conjugacy class of G. I'll put a representative for each column, for each class. Then we'll also put a number over each class telling the number of elements. So we compute when, for instance, we're using the L2 norm, we use these numbers to weight our sums. So for instance, let's check that we have an orthonormal basis here. If I take the inner product of chi triv with chi of pi 2, okay, well, we're just going to line the rows up. So I'll have a 2, a 0, and a -1. But then I have to weight by the numbers up top. So I'll have a 2 and a -2 to get 0. And we see that these characters are orthogonal. On the other hand, if I take chi of pi 2 with itself, okay, we have the 1/6 for the order of the group. The 2 squared goes to a 4, we have a 0, and then the -1 goes to a 1, we put a 2 in front, I get a 6, and a 1 comes out. So this is a unit vector. Now, for our proof, what do we want to do? We already have an orthonormal set, so I just want to show that we have spanning for the class functions. The way we do this, we're going to take, okay, our Peterbile result, the completeness result for L2 of G, on each G cross G representation, V tensor with its dual. I want to show that there's exactly one class function corresponding to each of these, and that subspace is just going to be, okay, the span of the character for pi. Let's consider the action of conjugation on L2 of G. So we have the right action, we have the left action. We can put them together to get an action of G cross G. We can restrict to the diagonal to get conjugation. So I'll call that C of G. Now, C of G acts trivially on the class functions. So note, if we apply C of G to F, evaluate X, we conjugate, and then because we have a class function, we can ignore the conjugation, giving us back F of X. So trivial action. Let's check that our characters are class functions. So if we apply C of G, okay, we're going to conjugate. Then we just want to show that this is equal to chi of pi at X. So we write out the definition. We could factor because we have a homomorphism. And then a property of trace is that trace of AB equals trace of BA. So I can push these first two terms past the third, okay, in order, and then the G's cancel, leaving us with the character of pi evaluated at X as desired. So the characters are going to contribute trivial types to L2 of G under conjugation. Now, we appeal to our completeness result for L2 of G and consider each irreducible block of matrix coefficients. Now, conjugation is going to correspond to the usual action of G on V tensor with V star, and this is going to be equivalent to Hom from V to itself. So we're looking for trivial types inside of these spaces. Now, the trivial types over here under the usual action are just going to be the intertwining operators from V to itself. So if we're considering an irreducible block, okay, our pi V is irreducible, Schur's lemma says that this space is one-dimensional. So coming from each irreducible block, we're only going to have a one-dimensional space of class functions. We already know that comes from the span of the character for the irreducible, and that's going to be our result. Now, let's verify that the irreducible characters classify the irreducible types. So, we have pi V, pi prime, V prime irreducible representations. If pi prime are equivalent, then they have the same character. Conversely, if they have the same character, then we can construct an equivalence between them. For the first statement, okay, we're assuming there's an equivalence, so that's some L carrying V to V prime. It's a vector space isomorphism and an intertwining operator. We rewrite the intertwining operator property as follows. So I have pi prime of G equals L pi of G L inverse. We take the trace of both sides. Now that gives character of pi prime on G, okay, with the definition. We substitute. Then I could switch L pi of G with L inverse. The L's cancel, and then we have the character for pi at G. So the characters are the same. Conversely, if the characters are the same, okay, we've noted, I could write this character as a sum of matrix coefficients for the corresponding representation. So if we consider the span of the character under the right and left actions in L2 of G, we're going to recover the irreducible block of matrix coefficients. Now, we're going to construct a family of intertwining operators. We'll use this property to show that at least one of them is non-zero, and that'll be our equivalence. Now, we choose orthonormal bases, ui, vi, for v and v prime respectively. Then we construct our family of intertwining operators, carrying v to v prime. Now, each of these, okay, straightforward to verify that each is an intertwining operator. And then if we consider, okay, t sub ij against uk vl, when we compute, we get this term, which looks like something from our Schur orthogonality relations. Now, we can't collapse this because we don't have these terms in the same vector space, but not a problem. Okay, what we do know that these are going to form a basis of our matrix coefficient space as we let J and L range. These give a basis for our matrix coefficient space as we let I and K range. So for some I, J, K, and L, we have to have at least one of these non-zero. So that's our result. Now, where did the t sub ij come from? We're expecting that pi and pi prime are equivalent. So I'm going to replace v with v prime in this irreducible component in L2 of G. Typical element here looks like this. To get an intertwining operator, we want G to act trivially, so we'll apply the group action and then average over the group. So that looks like this. I push the pi G inverse to the other side, and then we have t sub ij. Another consequence of our theorem, okay, we have Fourier's trick and Parsifal's identity. So the irreducible characters give us an orthonormal basis of the class functions. So that says each f that's a class function is a linear combination of these irreducible characters. We get the coefficients by taking the inner product of f with the irreducible character. Then we have Parsifal's identity. So if I want the length squared of a class function, I'm just going to sum over squares of the moduli of our coefficients. Now, this is actually very useful. So if we return to the problem of full reducibility, okay, so I'll have some representation pi v. We decompose v into irreducibles. Now note, that means I could choose a basis such that pi of g is represented by a block diagonal matrix. And then each of these are irreducible. If we take traces, then the character for pi of g is just going to be the sum of the characters on each block. So that looks like this. If we collect the characters for all the types that are the same, we get this here. Now, the n sub sigmas are what we're calling the multiplicities of sigma and pi. Okay, so the multiplicity is just going to be the number of these pi sub i's that are equivalent to sigma. Formulas. So using Fourier's trick to get the multiplicity, we're just going to take the inner product of the character of pi with the character of sigma in L2 of G. If we take the inner product of the character of pi with itself, we're going to get the sum of the squares of the multiplicities. Let's revisit a familiar example. So we have G equal to S3. We have the usual action on C3. So we're just permuting the standard basis vectors. We want to compute the character. So what we'll do, we're going to consider the trace of pi G, where we pick one G from each conjugacy class. So for the identity, we take the trace, we get 3. Okay, it's always the same as the dimension. For 1, 2, we take the trace, we get a 1. For 1, 2, 3, we take the trace, we get 0. So we have the character. Now we already know the answer here. We decompose this into a trivial type and an irreducible representation of dimension 2. Let's verify this using characters. Now, we set up our character table. First row is the character of interest. Let's first check the sum of the squares of the multiplicities. Now, for that, I'm just going to take, okay, our character inner product with itself. So we're going to have 9 plus 1 times 3 is 12, divided by 6 gives 2. The only way to write 2 as a sum of squares is as 1 squared plus 1 squared. So we have two irreducible types, each with multiplicity 1. If we use Fourier's trick to check multiplicities directly, okay, for the trivial multiplicity, we're going to take the inner product of rows 1 and 2. So I have 3 plus 1 times 3 is 6, plus 0. Divide by 6, I get a 1. So the trivial type occurs with multiplicity 1. For the sign representation, same calculation, except we have a minus 1 here, so a 0 comes out. So no sign representation. Finally, for pi 2, take the inner product of rows 1 and 4. Okay, we're going to have a 6 plus 0 plus 0. I divide by 6 and I get a 1. So the irreducible representation, dimension 2, occurs exactly once, confirming what we already knew.